Hello students, today I'm going to discuss a very important topic that is elevation of boiling point, which is coming under chapter solution. So this elevation of boiling point is basically a colligative property. Colligative property means a property which depends upon the number of moles of solute particles, and that property is independent of the nature of the solute particle. So we may have any kind of solute particle to make solution, but that elevation is coming out to be same. That is why elevation of boiling point is colligative property. This elevation of boiling point is also known as ebullioscopy. Ebullioscope is basically an apparatus which is used to find out the boiling point of different solutions, and the whole system which is involving this, the whole process is coming under ebullioscopy. Now let me give you the proper meaning of elevation. In order to understand this part, I have drawn a graph of vapor pressure versus temperature. Let us take a case of a solvent, and I have drawn a line here which is showing variation of vapor pressure of that particular solvent with temperature. Now you can see well that vapor pressure of this pure solvent is rising with temperature. So we know what is vapor pressure of our solution. We have already discussed vapor pressure. And if we want to know the variation of vapor pressure of solvent or any liquid with temperature, then that can be determined with the help of an equation, that is log P2 by P1 is equal to delta H vaporization, where R is a gas constant and T1 and T2 are two different temperatures. So if we know the vapor pressure of a liquid at a particular temperature, we can find out vapor pressure of liquid at any other temperature by using this equation. This is a very famous equation known as Clausius-Clapeyron equation, where delta H vap is enthalpy of vaporization. So we must know enthalpy of vaporization. So what I want to say is that vapor pressure of liquid rises with the rise of temperature. Now you can see here is a point A, and I have mentioned this pressure to be P naught here, which is actually 1 atmosphere. Now from this part we can explain the boiling point of a solution or a liquid. Boiling point of a liquid is basically a temperature at which vapor pressure of the liquid becomes equal to atmospheric pressure. Say we know that normal pressure is 1 atmospheric pressure, and when vapor pressure of that liquid becomes equal to 1 atmospheric, then at that temperature that liquid will start boiling. So you can see at point A, vapor pressure of solvent A is 1 atmosphere, which is 760 mm of mercury, that is height of mercury. So I represent this by T naught. The T naught is the boiling point of pure solvent. Now we have already done one issue, that when we add non-volatile solute to a solvent, we feel depression in vapor pressure of that solvent. That decrease in vapor pressure of a solvent in solution is known as a lowering of vapor pressure. So when we add non-volatile solute to a solvent, there is lowering of vapor pressure of solution, which is known as relative lowering of vapor pressure. So if we want to recall that, we know that P naught A minus PS over P naught A is equal to XB, which is equal to NB over NB plus NA. So when we add a non-volatile solute to make a solution, there is a decrease in vapor pressure of that solvent. So that is why I have shown this line here, and you can see that at any point, say I want to take T naught is the temperature, and at T naught temperature, pure solvent has vapor pressure P naught, but solution 1 has vapor pressure P1 at a temperature T naught. So students, you can analyze this is lowering of vapor pressure. So in the third graph, I have taken another solution with the same solvent, but by increasing the amount of non-volatile solute to it. So with that, I got a second solution which is having more amount of non-volatile solute, and you can see that line is lying below solution 1, means there is a further decrease in vapor pressure of the solution. So we can then analyze that there are three curves. First curve representing pure solvent, second solution 1 in which some non-volatile solute is added, and third case where more non-volatile solute is added to the same solvent. So if we see these graphs, we can easily compare that solution number 2 is showing the minimum vapor pressure, and definitely this solution will boil only when the vapor pressure of solution becomes equal to 1 atmospheric pressure. Now students, you can see well that this line is touching 1 atmosphere at point C. It means this C, corresponding temperature to C is T2. So T2 is the boiling point of solution 2. And this term is very clear that T2 is higher than T1 and T1 is higher than T0. And the difference is known as elevation of boiling point. Now in order to get result for this, we assume solutions to be dilute solution. So we consider ideal solutions. As we already know that whenever we talk about ideal solution, it means that must be dilute. So this is a requirement for making an ideal solution. Take a dilute solution. So with dilute solution, we can assume these lines to be linear. So we can see from here, from triangle ACE and triangle ABD, since I assume these lines to be linear because I'm taking dilute solutions, these are similar triangles. Since these triangles are similar, so I can say AC over AB is equal to AE over AD. Or I can simply say T2 minus T0 divided by T1 minus T0 is equal to AE divided by AD. Since these triangles are similar triangles, so can I say that delta T is proportional to delta P? Because what is AE? This is P0 minus P2 divided by P0 minus P1. So this is coming out to be delta T is proportional to delta P. So how much is change in boiling point? That is proportional to change in vapor pressure of the components of the solution. Now students, we know from Raoult's law, this is Raoult's law, I'm coming to this point again, that P naught A minus PS over P naught is equal to NB by this. Can I put this to be delta P over P naught A is equal to NB over NA if I consider this solution to be very dilute. This is for very dilute solution. So I can neglect NB for a dilute solution and I can write this to be weight of solute over gram molecular weight of solute. Weight of solute over gram molecular weight of solute. Now students, I can rearrange this to be delta P is equal to WP over MB WA. I have brought this P naught here. Now you can see that I have taken a solvent, a particular solvent, and P naught A is vapor pressure of solvent in the pure state. Ma is gram molecular mass of the solvent. These terms are constant. So can I represent delta P proportional to WB by NB into 1 by WA, right? What is WA? That is weight of, remember, solvent. Now since we know delta T is proportional to delta P, see this, delta T is proportional to delta P. So instead of delta P, I can put delta T proportional to WB by MB into 1 by WA. So term is very clear that now if I remove this proportionality, sign of proportionality, I can replace it by some constant. Say I call this by K WB by MB into 1 by WA. So students, this is a general result for this expression, that change in boiling point, that elevation in boiling point is equal to some constant weight of solute by molecular mass of solute, that is moles of solute, into 1 by WA, that is weight of solvent. Now I consider the first case. If NB, that is number of moles of solute, is 1 and WA is also 1, then that delta T is equal to K. So now what is K? K is some constant. I represent this by elevation constant. So K is what? An elevation constant. Now how can I define this? This elevation constant is elevation in boiling point. I repeat, this elevation constant is what? Elevation in boiling point when we have 1 mole of solute dissolved in 1 gram of solvent. So elevation constant is a constant. It is the elevation in boiling point when we dissolve 1 mole of solute in 1 gram of solvent. So it means delta T is equal to K. Let me call this equation as number 1. So I have defined term elevation constant. Now I am taking second case. If NB is 1 and WA is 100 gram. Now in this case, I can say delta T by taking equation 1, K into 1 by 100. Is that right? Now this K by 100 is equal to, say I define it by a new term, that is K dash. Therefore, how much is K? 100 K dash. I highlight this K as this by this way. Now you put down the value of K in equation 1 by using equation 1. Delta T is equal to, what is K? 100 K dash. Can I say K dash into WB by MB into 100 by WA. So students, remember this is a new constant. What I did, I simply consider value of K as 100 K dash and I replace this K by 100 K dash. So K dash comes here and 100 here, so I got this equation where K dash is known as molecular elevation constant. So students, first term was elevation constant. Now I am replacing that K by K dash, which is molecular elevation constant. And how can you define K dash? It is the elevation in boiling point when 1 mole of solute is dissolved in 100 gram of solvent. You can see this again. I am taking number of moles of solute to be 1 and W is equal to 100 grams. So elevation of molecular elevation constant is what? It's the elevation of boiling point when 1 mole of solute is dissolved in 100 gram of solvent. Now I am taking third case. If NB is 1 and WA is 1000. Now put down the values. This delta T is equal to K by 1000. Just by using equation 1. And I say K by 1000 is equal to new constant, say KB. Now, what is KB? It is basically molar elevation constant. Right. Then, what is K then? Definitely this is 1000 KB. Now, put down the value of K in equation 1. I write by using equation 1. Delta T is equal to KB into WB by MB into 1000 by WA. So simply I put this value of K in equation 1. So this is KB into WB by MB into 1000 by WA. Now student, if you see this term properly, don't you feel this is molality? Number of moles of solute dissolved per kilogram of solvent. That is molality. So I have simplified this, that delta TB is equal to KBM. Now I may write this to be delta TB, which is elevation of boiling point, and I want to say that the delta TB is proportional to molality of that solution, where KB is a constant known as molar elevation constant, or this is also known as bulioscopic constant. So remember, you can well judge why do we call this as a molar elevation constant. Now I have given you detailed explanation of elevation of boiling point. In books normally we see that the result is given that delta TB is equal to KBM, but we fail to understand why this is delta TB is equal to KBM, because this KB is meant for 1 molar solution. KB is considered when we take 1 mole of solute is dissolved in 1000 gram of solvent. That is why we call this as molar elevation constant. Now it has become very easy for us to understand the whole concept. And why do we use this formula that delta TB is equal to kBm? And earlier I mentioned that the elevation of boiling point is a colligative property. So what do we mean by colligative property? Property which depends upon the number of moles of solute. Now you can see that delta TB is equal to, I'm rewriting this equation, into number of moles of solute per kilogram of solvent. See, this NB, elevation of boiling point, is depending on the number of moles of the solute. I do not mention here which solute. So it is not concerned with the nature of the solute. It is concerned with the number of moles of solute. Remember, I want to say one thing very important, that this is for normal solutes. So exception is abnormal solutes. So when we consider abnormal solutes, you will come to know these things in my next lecture. Abnormal solutions means we do not consider those solutes which undergo dissociation or association. So this is meant for normal solutes which do not show any change in the solution. They do not undergo association or dissociation. So this is about elevation of boiling point, very useful. And if we consider it for your UGC purpose or for any purpose, for competitive purpose, we get molecular elevation constant. Let me show this molecular elevation constant. So just read the statement properly, that whether molecular elevation constant is given or molar elevation constant is given. If molecular elevation constant is given, then we will use this equation. So this is, you have to be meticulous while doing sum, whether molecular elevation constant is given or molar elevation constant is given. So in order to make this thing clear, I want to give you a very simple example. You must have seen, whenever we boil eggs, what we do, we generally add some non-volatile solute into water. What is the purpose of adding that non-volatile component? Obviously, when we add non-volatile component to water, we observe elevation in boiling point or elevation of boiling point of that solvent. Just like this, I'm giving you example just to make you clear the meaning of these graphs. This is for pure solvent. When some non-volatile solute is added, vapor pressure will go down. And when vapor pressure will go down, it means we need to heat that solvent more in order to boil that solvent. So whenever we add non-volatile solute to a solvent, we observe an increase in boiling point, and you can see that this solution 1 boils at T1 and solution 2 boils at T2. So you can observe the difference in boiling point. So I have made this derivation very, very simple, and in my next lecture, which is really very interesting, I will discuss next colligative property, that is depression of freezing point. So it's better to recall the things again and again. Thank you.